Hello, everybody. Thank you for joining our session. It's a hard choice. Nice weather, talking about Java in serverless. So, developers love serverless for its success. Fully managed, highly scalable app platform, support for open standards, easy developer onboarding, and security offered by the infrastructure. With it, there are some challenges. To improve performance, we usually can only add CPU and memory. We cannot log into a server in serverless and start tweaking the things around. There are predefined computer configurations. Scalability control is driven by metrics. And there's the issue of cold starts, the initial container boot up. Now, what are we going to aim for today? We want to understand what can trip us up. Then we want to know what to optimize for in serverless. What can and what should we adopt today for serverless Java in production? And then there's also Kubernetes. Does the same apply there? I'm Dan Dobrin. I'm an app architect on the North American technology team. I work with customers in North America and around the world on building and optimizing high-performance applications, primarily Java, serverless, and/or Kubernetes. And this is my colleague.
Yeah, I'm Abdel. I'm a cloud developer advocate working on the Kubernetes team. You can judge by my hoodie. I co-host a podcast called Kubernetes Podcast by Google, and most of my work is around containers, Kubernetes, and service mesh.
Okay, so let's get started. Today we want to, we work for a cloud provider, but we want to keep it practical. We want to talk about performance, but in a serverless environment. So we want to leave you with some practical guidelines, and we'll run demos in the cloud. So let's start from the basic arithmetics. Optimization in serverless is a simple sum of the cloud runtime environment, your Java runtime, the frameworks you're using, whether you Spring or anything else, your dependencies, as well as your application code. We cannot handle or optimize each one in isolation. So in my engagement with customers, developers are asking me many times, why do services start slow in serverless? Is it Java? What is it? Why do I see a high number of service instances? My container is not accepting traffic. Is there a optimization, like a magic button? And even if there is, how should I think about optimization? Do you have any ideas? So as we're building 15-factor apps, yes, there are 12, now there are 15, and API first, which was added in the last 3, is really helpful in when building serverless applications. We're always thinking, what would be important? So if you would pick one, which one would you pick? Which would you think would be important to you? So let's think about this. We talk about scalability a lot, so disposability should come into play. How do we handle gracefully shutdown and startups in our application? It's a distributed system. Failures can occur, so we're not building a robust system, we're building anti-fragile systems. Now, as we're looking into optimizing our application, we're always looking to find a balance. Should it be startup? Should it be throughput? There are many other aspects in between: resource consumption, concurrency, container images. But we should not forget one thing. We need to understand how to find a balance. We need to understand what our requirements are. What SLAs do we have our application? Because before diving into different techniques which could optimize performance, we need to know what we're actually aiming for, because many times we have simple solutions which are available to us, and we can apply them, and maybe that buys us time to build a higher level of optimization into our applications. So let's just be aware that the problem of scale to 0 is the same as scale up when it comes to cold starts. Whether we scale up from 0 to 1 is the same as from 10 to 11. There's absolutely no difference here. And scaling up in a serverless environment is influenced by several factors. We're going to use today Cloud Run, which is Google's serverless, containerized serverless offering. It is an implementation of a clean implementation of Knative with some additional feature. Consider it Knative plus. And we're going to see how those features help us. So to auto-scale our environment, Every instance will scale up when CPU reaches, for example, a certain request. In Cloud Run, it's 60%. Will it scale up with one or more? Depends on the influx of requests. Cloud Run might start multiple instances for you, but we encounter cold starts each time. It's also influenced by the minimum number of instances which we could provision. We might expect a certain threshold float, so we might say we always want 5 up and running. But we also want to cap it for costs or for security reasons at a maximum number of instances. And we also want to think about request concurrency. Why is request concurrency important? We should not equate one request with one new instance. As we're dealing with a containerized Java application, in our case, we can run multiple requests to be served by the same instance. Therefore, we will encounter less cold starts than if we would bring up an instance for every single request. One major improvement which is specific to Google, which was brought for Java because of reflection and dynamic proxying, also for Node.js, but Node.js is single-threaded, so the impact is not as high, is CPU boost. It will increase your CPU at start time until a startup probe succeeds, plus the first 90 seconds. By this, it will decrease your latency significantly, and we want to see that in action. Now, before we want to see how all these, we would say, traditional optimization techniques would work, let's revisit a number of things which you could use as practical guidelines for your applications. So let's start from the cloud runtime. You can increase the allocated number of vCPUs. You can use a different runtime environment. Gen 1 in Cloud Run is focused on startup. Gen 2 on faster processor and a network file system. You can use a CPU boost for your application. You can tune your minimum instances. Do it proactively, but do it wisely, because if you over-provision, there is a cost, even if it's a pay-per-use. And then you want to match memory to concurrency. We should not expect that more requests will not consume more memory. If we look at the JVM, there are some very clear guidelines which we can follow. Always use the latest LTS version. We are in an enterprise, and enterprises will run on LTS versions. Don't rely on default Java ergonomic. Just set them yourselves. For example, set memory as a percentage of container memory. If you don't set it, you'll get 25%. Set max RAM percentage to an 80%, maybe 75%. You can hardly go wrong to start with it. Set a garbage collector explicitly, because if you set it below 2 gigs, well, 1,768 megs, you're going to get a serial garbage collector. So set it explicitly and reduce the thread stack size. It will reduce your memory consumption, especially on highly concurrent requests. Now, optimize Spring Boot, limit unnecessary auto-config, optimize the class path scanning, the dependency management, and also disable, we like all the actuators, but disable the actuator endpoints which you don't need. Last but not least, it's your application. No optimization would help if your application will not be optimized. So minimize the container image, layer your images as you build them, eliminate any unnecessary dependency, and avoid calling other services during startup. Yes, it's for all of us who worked in the app server days, that was something which we did at startup, call other services many times or load data from the database. So let's try these things out. I picked a quotes application. It will give you quotes from famous people, and deployed it in with multiple configurations, with one CPU and 1 gig of RAM, then 2 gigs, 1 CPU, but using CPU boost, and we want to see how it compares with 2 CPUs. And we want to deploy it on 2 different runtime environments in the cloud. One runs in Europe, one runs in US Central. So to run all these tests, we're going to run them. So let's see a few things. When we run in the cloud, we're not looking at the same numbers. Oh, we run it on our M machine and we applications start faster. We need to take into consideration what other factors could come in. And if we look at our deployment in the two regions, we can observe that we can look at the deployment, which you could see. It is still respecting the Knative spec, to which different features are being added. It uses immutable revisions, and you can see every single parameter you can configure. Now, startup CPU boost is a simple parameter which you would be running. We can just enable it and see it in. It is just one enabled parameter. I'll make this too large. So we can do that. Let's see. Our tests are soon going to finish. Now, when we look at these numbers, let's not look at them as absolute numbers, because we deploy in different machines. There's an influence on the security installed on my machine, which will scan the request, the slow Wi-Fi, many other factors which come in. But we want to see a gradual improvement. And we also want to see if we didn't make any mistake in our application. So let's grab the logs. And the logs will be available. The top part runs in Europe on a Gen 1 type of environment. The second one runs in US Central in Iowa. So we want to compare the numbers. So if we set up 1 gig of RAM and 1 CPU, it starts 19 seconds. If we add memory, there's not much of an influence for the startup. And we can compare that against the two different machines. When we add CPU boost, we can see a significant drop in, and it depends on the machine which you're on. In Iowa, it runs on Gen 1 machines, which are starting faster. If we compare it with adding 2 gigs of RAM, numbers are similar to CPU boost, so you can see an equivalent behavior. When we add tools, so we can set up a number of parameters. We set up the garbage collector, we restrict the thread size. We can see a further improvement in our application. And after some point, there's a point of diminishing returns. If we add 4 CPUs or 4 gigs of RAM, it will not bring us much benefit. So once we explore these aspects, let's see what is our next step. So the first one which comes to mind is class data sharing, which is a JVM feature. It helps reduce the startup time and memory footprint between multiple JVMs. The class metadata is cached in an archive, which is then preloaded quickly into a JVM instance. It will cache both your application classes as well as system classes. How does this archive get built? It relies on a training run to exercise the startup and warm up code passes to be captured. Now, why should you use it? It's a production ready, it's a mature technology. It showed up first time in Java 5. Now, AppCDS has a good improvement for security. It does not cache the initialized values of static variables, which could be a problem in other environments. And it's more secure because there's no risk of leaking secrets in the CDS archive. It caches class metadata. And there are less constraints and side effects than GraalVM or Project Crack. Now, how is AppCDS working in Spring? It's developer friendly. There are great improvements which were brought last Thursday when Spring Boot 3.3 came out. We know that, and it's well documented, Spring applications start faster if they are layered. So the Spring Boot default unpacked layout at this time is optimal, and it is CDS friendly. How can you collect your archive? You can start the application, and there is a flag available in Spring. It's valid for Crack, it's valid for CDS. And as soon as it starts loading your classes, it will stop before going and actually initializing your application. And it creates the CDS archive on exit, which we will use to build in our container image. Are there any trade-offs? Well, the improvements are not as significant as GraalVM or Project Crack, and what it requires is that the JDK, which we used to collect the archive, and the class path used in the archive creation have to be identical to the one at application startup. But sometimes our application don't want just an incremental improvement. Sometimes we have application and services which have very strict SLAs, let's say below the magical 1 second. And here we need next level performance. So if we can compare JIT versus AOT. So in traditional Java application, you have a Java class, you compile it to bytecode, archive it, and containerize it, and then run it at runtime, where the JVM will interpret your bytecode, and as you execute different code passes, Hotspot will transfer some into native code. So less work if we look at it graphically, less work at build time, more work at runtime. When we build native images based on ahead of time compilation, the process of compiling code into a jar archive is still the same. But then we're building a native executable. How do we do that? We analyze the code starting from the main, and we are moving runtime optimization at build time. So it makes closed world assumptions at build time into how for execution at runtime. Now this execution is a constraint on Java Dynamism because the class path is fixed, and what we have in the image are only the classes which we know about at build time and not at runtime. But on the other hand, and that takes also time, but on the other hand, the execution environment is much faster because an image is just started. So native images are self-contained executables. They're built from Java apps. They run without a need of a JVM. They're based on a runtime system called Substrate VM. The project is based on Oracle GraalVM. It is specific to the individual OS and machine architecture where you're going to run it. And they're compiled ahead of time. Now, the images, because we have only the classes we need, are smaller. They consume less CPU. Therefore, they're greener too. So why should you use native images with GraalVM? Super fast startup. The peak performance from the first request, request 1 versus 10,000, will be executed at the same speed. The images are smaller. You use less CPU, and you're loading less memory. The RSS memory consumed is much lower, therefore leaves more room for your application. And it's a smaller, from a security perspective, a smaller attack surface. Now, are there any trade-offs? Well, yes. The analysis takes time, so the compile time depends on the machine you run, an M machine, on a beefy Linux. Could be from a minute or two to maybe sometimes several minutes. It does closed world optimization assumptions with ahead of time. And for libraries, some older libraries or some third-party libraries, there you have to add additional metadata, which building the native image by itself cannot identify. Now, is there an alternative? Is GraalVM the only, and building native images with GraalVM our only option for super fast startup? So the alternative would be Project Crack. Building at the build of the application of the archive is the same thing. You build the application, here's the jar archive, you start it in your environment in which you're going to execute it. The difference is that you start the application, and as it is started, you you checkpoint the application, and you collect a snapshot. That snapshot, it depends. You collect it when you start the app, you run some request, that influences its behavior, and then you restore it at runtime. Now, why should you use Project Crack? It's the same super fast startup time. You reach peak performance from the first request if you checkpoint a fully warmed up image. I mean, an image which is started and you run a number of requests through it. The developer onboarding is easy because you don't have to deal with shared metadata at this time. But you do have to implement a number of interfaces. Because Project Crack is it's required to checkpoint and store the Java application up front. Then the peak performance depends when you actually collect it in the app lifecycle. Then objects, database connections, file handlers are objects. They need to be closed and they need to be restored when we restore the image. So we have to implement a couple of interfaces which gives us the opportunity to address these problems. Now you can run it only on Linux because Project Crack depends on Linux CRY-O and it has that as a dependency. Sensitive data can potentially leak into Snapshot. If you think about it, a secret, you configure a secret and now you have a secret baked into your image. Or you assign a static final with a random number generator and then, lo and behold, every single restored image will issue for you the same sequence of random numbers, which is probably not really desired. So let's run our application and let's see how CDS would work in here. And we're going to run this in both regions. So we run this. Well, I'm going to anticipate running one more because I run it via a script, but we're just going to look at numbers for CDS and native at this time. So as we we want to run our logs, and let's ask for the same logs we ran before, just so that we can see them via comparison. So with CPU boost, we were at like 14 seconds. We got it down to maybe at like 8 seconds. Now, with class data sharing and the improvements brought in with Spring Boot 3.3.0, we can bring it down. It collects the last 100 entries from cloud logging, so sometimes you see 2 entrances for that. So it brings it down now to like 3-4 seconds. And a native image comes down to 2 seconds. So where is that 1 second? Well, we talked about that we can optimize each level, but here we purposely left a mistake. In the image, I left an in-memory H2 database and a flyaway to set up a schema. Should I have done this? No, but these mistakes can happen. So it's on us to proactively correct that. So we're looking at 2 seconds, not at the sub-second which we wanted. So let's look into what is next. Well, we talked about startup, but how about peak performance? Many of our services in serverless require longer running time. For example, you do a bin packing algorithm. It could take 5 seconds, but it could run for hours. Or you run a credit check in a bank, and it will contact 3 credit rating agencies. And then you'll see if you can get a particular loan or a credit card. So all of these will run longer. So here, peak performance under heavy load becomes important. So one option which we have, which was added by the Graal team, is profile-guided optimization. So if we think about this, the JIT compiler has the ability to analyze the runtime behavior of the app. It acquires a profile of the app, which passes it to a tier 2 compiler. The ahead-of-time compiler does not have the profiling information because it makes closed-world assumptions at build time. So PGO gives the AOT compiler both a static view and a dynamic view of the application. So the end result is the optimized app performs better than the default AOT compiled app, and now you can have both sides of the equation, startup as well as peak performance, sustained peak performance. How would you get this? How do you get this profile? You would get this profile by running an instrumentation phase. Yes, it will lengthen your build time, and start your application, run a number of tests against it, collect that profile, and then build your final image. And the performance becomes quite spectacular. So I'm going to show this diagram courtesy of our friends in the GraalVM team. So how do we think in serverless? Most of the teams are usually starting with I start with 1 gig of RAM, 1 CPU, that's the default. Let's start with that. Many applications are like that before looking into, should I get to run larger images and make better use of concurrency, especially if I'm thinking cold start. So the Graal team collected these stats on the number of operations per throughput, so gigabytes over time, and they noticed that the GraalVM image performs significantly better in lower memory settings, up to 1 gig. Sometimes teams use 512 megs only, and it's always, even at larger heaps, it performs better than the JIT compiler. Now, before we will look at how PGO works, and we have to think about, is there always a missing link? And because we talked about, well, there's a drawback of the long running build times. So one feature which will be added by the GraalVM team is layered native images, and it's a very exciting feature if we think about this. In a closed world optimization, each time we build an image, we have to start from the same main, go through every single pass, and analyze every single layer. But what if we could take layered images like in CDS and build a base image out of it, and then construct our application? Could be a JDK base, a Spring base. Now we build GenAI, we could have Spring AI or LangChain, or we could have our own libraries. In an enterprise, we build many times cross-cutting concerns, which are like, let's say, PII data masking, or business auditing, or various other private libraries. And now, when we build a native image, all we have to do is build only the last layer, our application. This will bring down, we want to see it in action, but it will bring down build time to the seconds, the single-digit seconds. I would be very happy to see it at 1, 2, 3, 5 seconds, because then what is the difference of how we build our applications? Now, each one of these layers, as they're built up front, we cannot do the closed-the-world optimization of the whole app. So each layer would be a bit larger than if we take the sum of all, rather than the original just build a native app as we do it today, one single native executable. But think about it in the cloud. In the cloud, we share a lot of base images, same as we do with the container layers. And at scale, if we are thinking in the enterprise, there will be a significant benefit to us. So let's see how PGO comes into play. The QR code links you to the sample we use, and every single script is documented there, so you can try every single script in any kind of configuration. I hope that makes it easier for you. So let's actually we ran the PGO numbers. So now let's collect all the numbers as they come along. So now with PGO, and with PGO we bring down, this is running in the cloud in 2 different environments. We bring down an application down to 700 milliseconds, or in a Gen 1 environment to 500, 600 milliseconds. The second one, called PGO Full, is I applied CPU boost to it. So there's a small improvement even for a native image when we start that container in a serverless environment with CPU boost. So now we can get 500 milliseconds or 700 milliseconds, which now we're getting to numbers which we can actually, rally behind. And you can see this all runs into the cloud. You can see that you can build these applications. Now, what does the future hold? Project Layden, is this going to be the magic solution one day? Well, Project Layden focuses on improving startup, warm-up, and footprint of your application. It's built on this concept of shifting parts of your computation earlier to build time. Let's say ahead of time compilation to app CDS time. And ATS, different applications, constrain Java's dynamism. So closed world assumption do that. But there are trade-offs which we can very much, in most cases, can live with. The basic idea is that the goal is to preserve the meaning of the resulting app image as the original. And then you want to select which aspects can be shifted and which aspects can be constrained. Now, before we wrap up the serverless part, I want to show you also a Project Layden in action. So I built this with the Bellsoft distribution of Java 22, and it relies on, while sure it is pre-main, it is in the future, and courtesy to my former colleague at Pivotal VMware, Seb Deleuze, for the script, we can leverage building a CDS image of our layered app and pair that with ahead of time compilation, even if it's not a native image, just leveraging ahead of time as offered by Spring and building an image. So if we look at the performance here, the number already ran, so we get for a Project Layden instance, we get 2 seconds, we get 3 seconds of startup. So if the image is preserved, then again, we are talking about numbers which we can execute in the environment. So to wrap this up, which technology should you use? So if you were to have only one optimization, which you should do, of course, please don't call another service that's startup. If you would have one single choice, in our opinion today, for a serverless environment, running GraalVM with profile-guided optimization enabled with a G1 garbage collector, which will run on Linux. So PGO with G1 runs on Linux only. With Java 21, the latest LTS, and the highest optimization level in Graal, which is -03, is production ready, and we would recommend this for your production usage. Now, we talked about serverless and the different improvements, and we could see how by making different changes, performance gets better and better. But there's also Kubernetes, because their containers can be deployed in Kubernetes. Does the same thing apply to the same tenants hold? There are applications in Kubernetes which have the same requirements. So I will pass this on to Abdel, and he will explore this.
Thank you. All right, so switch your laptops in the middle of talk.
That's like a pit stop at a Formula One race.
Yes, what can go wrong? All right. All right, so let's do a quick recap on how resource management in Kubernetes works, right? So this is typically how your deployment in Kubernetes looks like. It's a YAML file, arguably the world's best programming language, and you just have a bunch of parameters, and then you have a resource section, and in the resource section, you specify requests and limits. So requests is how much your pod needs on scheduling, and the limits is how much it's allowed to consume. If you look at the 250M, it looks weird. That just basically means half a CPU, 1/4 of a CPU. Kubernetes has this way where it takes a CPU and considers 1,000 is a full core, so 250 is a quarter of a core. So the requests are basically what's used by the kubelet, which is the agent on the node to schedule the pod. This is the limit. What happens if you go over your limits? Well, if you go over your CPU limits, the application will be throttled. If you go over your memory limits, you will be killed, right? Because memory is not a compressible resource, while CPU is. So What does that mean actually for developers? Because when we show these numbers, most of the time people don't understand what we're talking about. Yes, there is actually, you can think about it as quality of service. If you specify requests and limits, you have a guaranteed QoS. Essentially, the scheduler will make sure that the node has those resources before it puts the node there. If you only specify the requests, this is an example where I have 2 containers. So you can look at the first one, the one that says Nginx 2. It doesn't have, Nginx 3 doesn't have limits, which means that this pod will be allowed to burst. It will be allowed to consume more resources than it initially requested, up to the point where the node itself doesn't have any resources anymore. And then again, if it's CPU, it will be slowed down. If it's memory, it will be killed. Best effort is when you don't specify anything, and that's basically kind of YOLO mode, right? Like we deploy the app and just hope for the best. That's not something I recommend in Kubernetes. There is only one use case where people use best effort in Kubernetes is if you are using a managed environment which has a built-in autoscaler and you want to warm up nodes to make sure that they're always available. What you do typically is you deploy pods, and we call those balloon pods. So you deploy them just to hold resources, to keep nodes available. So if your application needs to autoscale, those will be killed, right? So that's the only use case when best effort is recommended. Yeah, so the kubelet will evict the pod if there is node pressure, if there is especially memory node pressure or storage mode pressure. So typically speaking, the guaranteed is the way to go. Burstable is okay, especially if you are doing workloads that can like vertically scale, and best efforts not recommended at all. We talked about this. So how does that translate into containers? Well, if you deploy an app and then you use the command line on the, so Docker inspect or CRI-CTL, same thing, it will basically look like this. So CPU requests, that's 1,240. So it gives, so for 250, it does 1,024 times 0.25, so 256 shares. Same thing for CPU. And then memory will be translated into bytes and basically will be, it's just a number, right? So since version 8, actually I have to fix the slide, I think, or 10, is it 10?
8.
10.
8,
okay.
8 build 192.
Thank you. So since Java 8, Java is aware of container resources. So the JVM knows it runs inside the container, right? So there are actually 2 approaches to make your JVM startup faster on Kubernetes. You can just set higher resource, right? Basically over provision the application, and then you will end up paying for it. Yeah, you can like higher resource requests and higher resource limits, or you can set lower resource requests and then higher limits, and let the pod kind of burst within those limits. In both cases, you are gonna over provision your application. So the question is there a way where we can dynamically allocate resources to containers running in Kubernetes? And the answer is yes. In Kubernetes 1.27, there was a feature introduced called in-place resource resize, or in other terms, dynamic resource allocation. Before this version, if you want to resize a pod, you have to restart it. Now you can just add CPU and memory to a pod live. Now, there is a question of once you add memory to a pod, if it's JVM running there, how does the JVM pick that up and changes its parameters? That's still in the working, if you want. And so the way this looks like, so you can basically, resources now are immutable, so you can change them. And you can also set a policy to say, if I change CPU, do I want to restart or not? Or if I change memory, do I want to restart or not? So this is introduced in Kubernetes 1.27. This is the feature. And you also have the status. So the pod will reflect if it has been resized, right? So you will have resize in progress. It will say no in progress or completed. So this creates a lot of possibilities for us. One of them is being able to do vertical autoscaling, right? Just increase the size of the pod, essentially. And the other one is what we took advantage of this feature, and we built something called Kube Startup CPU Boost. So what it is, it's essentially a CPU boost for Kubernetes applications that will CPU boost your application at startup time. It's open source, and it's available on our GitHub, and it's deployable on any Kubernetes cluster 1.27 plus that has that feature enabled, because the feature is alpha, and most cloud providers actually don't allow you to spin up clusters with alpha features, or if you do, they give you a lower SLA. On Google Cloud, if we spin up an alpha feature, we will enable all the alpha gates for you, and we delete the cluster after 30 days, and the SLA is lower. But this is open source, so you can deploy it on any Kubernetes environments. So how does it work? Well, basically, before the pod is scheduled, we go through the scheduler, we run a manager, the manager will look in the cluster if there is a CPU Boost object deployed, if there is a definition deployed, and if it is, it will change the configuration of the pod, right? So this in Kubernetes world is called the mutating webhook if you want. So it will change the resource requests before it passes the pod to the scheduler. So the scheduler is aware or knows that this pod needs whatever requests plus the boost value you defined before it schedules it. So this is how it looks like. I'm going to show you a demo. You have a CPU Boost object. You basically add a selector, so that's how you say which pod to target. You add a policy if you want. That's basically where you say what's the percentage. So 50 basically means 50%, so add 50% CPU. And then you set also a condition. And the condition is when you say, when do you want to stop boosting the application? You have two ways for setting a condition. You can either set it on state, read it through, or you can set it on a time, 60 seconds, 120 seconds, something like that. I'm going to skip through these details. I'm going to just show you quickly how it looks like. So I have a very simple deployment here. It's basically the same app that Dan was using for the demo. It has one replica, and if we scroll down here, it has, what are the resources? Sorry, yeah. It takes basically 500, so half a CPU and 512 megabytes of memory, and then the limit is one CPU. So if I deploy this application here, so if I deploy it and look at the pod, just wait for it to be ready. I should take 1 second. So once it's ready, I'll just grab the logs and look at the startup time for the app itself. So I think I can already do that. kubectl logs. I'll see that my app started in 13 seconds, right? So the app, you can see it over there. It's in the bottom corner, but basically it started in 13 seconds. Even if you don't see it, just believe me, I'm not lying to you. So now let's do something. Let's basically take this app, delete it. I will deploy the CPU Boost first. So I have I want to deploy it. So I have the CPU Boost object here. It's basically, it does 100% increase, so it will double up the amount of CPU the application have. And it uses a selector. And this is basically just the key value for the label that I have on my application, which is somewhere here. This is the actual label, so I just match the label. Then once I deploy it, I can actually get startup CPU Boost, it's called. One interesting thing we added here is we added a status to it, so you can see if it's actually working, if it's doing anything. You can see in the bottom, it says it's ready and it's active, can boost new containers, so it haven't done anything yet because I haven't deployed anything yet. But if I deploy my app one more time, and then recheck this, it will say total container boosts 1. And then if I go and check the logs of my app, I should see that it started at least 2 times faster. Should say here somewhere, yeah, it started in 6 seconds instead of 13, right? So basically I just boosted the application by 100% of CPU during the startup time, which allowed it to start faster. And basically, of course, once the application is boosted and it's ready, then the CPU Boost manager will go back to the container and take out the extra CPU it's allocated. So it will just, in my case, it will go back to 512 milli CPU that I assigned it first time. This is a QR code if you want to, this is a blog we wrote, so if you want to take a look at the blog. And I'm going to leave it up there for a second. And yeah, that's it. I did the demo. And time for questions, I think. I hope this was useful and we were on time. So thank you very much. We should also check the app if there was any questions, but we can take live questions.
Yeah, absolutely. Yeah, please go ahead.
I have one question. Have you guys thought about a situation when you want to keep your pod offline and only make it available when you got a request incoming or something like that? So something on your cluster, on your Kubernetes that is available like in AWS and Azure and et cetera, et cetera.
So yes, there are a few features being discussed. This is all being discussed in the public. Kubernetes has a concept called KEP, kind of like Java, like Kubernetes improvement proposals, and you can find them on GitHub. But there is actually a feature being asked, which is to snapshot a container or snapshot a pod, so you can just make it sleep until you need it. And I experimented with it. I wrote a very simple tool called ZeroScaler, which basically monitors the traffic to your pod, and then if there is no more traffic, it just like pause it and then restart the pod when there is traffic coming. But we're thinking about it, but it's not there yet. Any other questions? Yes.
Please.
I noticed that when there is a CPU boost also for Cloud Run, which I really like.
Yeah.
There's also the CPU boost for Cloud Run, which is a product I really love. But I was wondering, I couldn't find any details on the pricing. How does the pricing work for the
So
option?
the pricing is basically doubles up your CPU at startup, and
Okay.
you would be incurring a CPU pricing for that portion of the startup.
Yeah, okay.
Nothing more than that.
Yeah, okay.
Now,
okay.
enabling it is one single change, and it will create a new revision. Another thing which like any change in Knative requires you to publish a new revision. But if you want to change your minimum instances, for example, you can do that as of last month in Cloud Run without incurring a new revision. So let's say you suddenly have an influx of requests for whatever reason, but you have 10 instances happily serving customers and you have 10 more. It's good to have good business. And you can just increase the number of instances while letting in-flight transaction also continue.
Yeah, okay. Okay. Thank you.
Sure. On Kubernetes, it shouldn't matter because you're already paying for the resources. The node is already provisioned. Unless you are using those like managed Kubernetes like Autopilot in our case or AWS Fargate, which then they charge you per CPU, then it will follow the same pricing model as Cloud Run. So, any other questions?
Yeah, please.
We saw the startup CPU boost. Is there, for example, also something for RAM? Or
For Kubernetes or for Cloud Run?
For Cloud Run, it does not change your memory. It does not change your memory setting. It just boosts the CPU. Because if we think about it, if you take a classic Java application, right, where do we spend most of the time? Dynamic proxying, reflection, serialization, and resources. So those are the features which would benefit mostly from CPU boost.
okay. No, I was just thinking if some applications need more RAM, like when starting up, besides like when running. So that was my thought.
No, so the memory settings you configure it and they remain set. And CPU boost is automatically adjusted down. So if you set up, like I said, 2 gigs of RAM, 1 CPU, it will boost it during startup. But after the startup probe succeeds, and you should really configure one in a production environment, plus 90 seconds, it reverts to your originally configured value.
So it goes back to the request.
To
Right?
whatever you specified initially.
Yes. All right. I think we're on time.
Yeah?
Thank you very much, and please
Thank you.
consider